So hello and welcome to the third week's lecture series on next generation sequence analysis. Today we'll begin two lecture series on the R statistical programming language. I thought I'd start here by just sort of illustrating why R has become so essential to the NGS analysis community. One is that it is under active development by statisticians and researchers in the field. It is basically the go-to place for sophisticated statistical analysis and graphical design in the NGS research community. Some of the things that are useful about R generally is that it has interactive usage options. It has its own well-developed, simple, and effective programming language, which makes it useful for custom analysis. That is writing of specific functions that do specific tasks. It has superior data manipulation capabilities. And lots of statistical and mathematical operations that are both part of the core and for more sophisticated analyses are developed by the community. So it is open source, so that means that developers, both in academics and applied settings, can develop resources that can then be shared with the rest of the community. Finally, it has some superior graphical properties which make it a go-to source for generating sophisticated and publication quality graphics. So there's a huge number of packages that are available. So one of the first things to familiarize yourself with when you're engaging in a new program is to really do a thorough search of the packages that are already available, because there's a good chance, if you're doing some of the common analyses anyways, that somebody has already developed a very nice package that will do the analysis or assist you with your analysis. So one of the things that you'll encounter with R is that it is very function rich. There's a lot of options, a lot of ways to configure individual functions, and the cost of that really is that you will have to seek help. The simplest way to seek help, at least for core R functions, so this is RStudio here. I'll be switching back and forth between the RStudio and the PowerPoint presentation. Hopefully that won't be too confusing. But anyway, let's just type read table, one of the common commands here, and you'll notice here that in the RStudio you have a nice interface here where you have the command line options on the left. We have the documentation here that I just requested on the right, so we can really type help for, or we can request here where the concatenate option here or function. I just requested help using the other syntax here, either question mark in the function or help and the function in this fashion, and you'll get a nice help window here. So in the help window, it's important you'll see the usage, which describes the function, several of the different arguments that are possible with that function, and their default settings. So here then they're summarized in words. This is how you would execute it at the command line, keeping in mind that the defaults are there for a reason, and so that you can simply type a function like cat without specifying all of the arguments, and you can obviously configure as needed. But here are the arguments. There's always a second section called the values section. So the arguments, the details about those arguments, and if you go down here, you'll get a section on values. This is what it returns. Okay, so in the case of cat, it returns nothing. Then it gives you some references and oftentimes some examples. Okay, so this is probably the simplest and easiest way for the base core functions anyways for seeking help. So let me find my slideshow here. So the other ways then is to search the R intro documentation, which I've put up on the website and is part of the reading for this week. It really is, it's pretty dense because it is documentation, but it's also there as a comprehensive introduction, which we don't have time to cover in our lectures. But that, really is the place to start with understanding R. Google, let's face it, sometimes the fastest way to find the answer is to search for the question on a message board that somebody else has already asked, and to basically see if the question's been asked, and then oftentimes you can get your answer right there. If the question has not been asked, you can go to the R listserv. This is an email group which you can send an email to. It's a very active group. I'm a member of it, and I get literally hundreds of emails a day about very specific questions related to R. So let's begin our discussion of R by talking about the variables and how you go about assigning values to variables in R. Seems like every language has sort of their own syntax for this. R is no different in that regard. You'll notice the assignment arrow, which is a little bit different in R. This is the typical convention or way of assigning values on the right to a variable name on the left. So this is something that is defined by the user. So here I've made up the variable name called numbers, and I've simply then assigned this vector of numbers with the combined function 1, 2, 3, 4 to that variable called numbers. There are some naming convention issues that are important to understand, like you can't begin the name of a variable with a number. Okay, that must be an alphabetic character. So typically, though, you can use alphanumeric characters for the remaining positions in a variable name. And then special characters are generally not permitted because they have special meaning in R. Two that are permitted that you can use are the underbar and a period. So there's a number of different types of variables in R. There's vectors, matrices, data frames, lists. There's additional ones that we won't be talking about in this class or using in this class, because most of the functionality you need for basic analyses are in this set of four sort of variables. You have vectors, which I've already introduced you to. In a second, I'll introduce you to these sort of types of vectors. But you have here, I've just made one called numbers with the combined command, another called characters, and one which is a mixture of numbers and characters. So this is really comparable to an array in other languages. In R, we call it a vector. So matrices are familiar to most people. These are two-dimensional vectors. You can initiate one simply by specifying a matrix plus a vector, but then you're giving the vector sort of two-dimensional definitions here with the n row and n col sort of arguments. So we can take the matrix, the vector numbers from here, and this would provide a 2 by 2 matrix with the numbers 1, 2 in the first column, and then 3 and 4 in the second column. So data frame is similar to a matrix. Actually, what I'm going to do is explain this, because in order to understand the difference between a data frame and a matrix, it's important to understand that variables have types, or more specifically in our sort of syntax, or what are called storage modes. So a vector, which is the simple array-like variable type, can be either numbers, characters, vectors, but it can't be both. Okay, so going back to the previous slide here, you can see here this is a numeric vector, this is a character vector, vector, and this is a mixture of a numeric and character vector. However, in our terms, this is actually becomes a character vector. So if I flip over here to the RStudio and just type here, let's make the variable here called numbers. And hopefully you can see this and it's not too small. I tried to blow it up a little bit. So here we have numbers, and if we type just numbers, we can, at the command line here in R, you can see that it spits out the vector of 1, 2, 3, 4. And let's do the same for characters. So the assignment arrow is simply the less than sign followed by a dash. Let's just go with three letters there. So now we can type characters, and you see ABC. Now let's try a mixture. So let's make a new variable called mix, and let's combine a number and letters, and now let's see what we get. Notice how it puts quotes around the ones. The 1 here keeps the A and B the same. That's because what it did is it coerced this numbers and mixture of numbers and characters into what's called a character vector. So the numbers simply become characters in this case. So the variables have to be one or the other, either numeric or character, and if you use a mixture, then the numbers and characters, it becomes a character vector. So logical vectors, this is a very important, which we'll talk about briefly later, about how important this is for subsetting. But logicals are simply trues or falses. Okay, so they're Boolean. It's basically a Boolean, presence, absence, 0, 1, true, false type of vector. And notice here that there's no quotes. So if there were quotes, it's simply around true and false. It would simply interpret that as a character vector, and it wouldn't have any special meaning. But true and false here are interpreted and have important meaning. They are not just word strings. Okay, so keep that in mind. And then finally, there's another class here called, or storage mode called factor. And really, you'll see this when you read in tables, and I'll show you how oftentimes it's useful to suppress character strings which are read in as factors when you read in a table, simply because factors are sort of have a special meaning in statistics. And so these are sort of the levels in a or factors in a sort of categorical analyses of, say, an ANOVA analysis of variance or other types of statistical analysis. So factors really, for a lot of the just basic manipulation of tables, unless you intend to do specific statistical analysis, the factor variable, oftentimes it's useful to treat the factors as characters. So then there's these very useful functions, which is what type of variable is a vector. Let's go back to the RStudio here, and let's use a few of these. We have type of, is.numeric, is.character, etc. So let's type is.character. So this is a function, is.character. So we could request help if we needed to for this function, like any other function. We could say is.character, and then we type the name of the vector called numbers. The answer is false. Is.character characters. True, it is. And is.character mix. Yes, the answer is true. So it's easy to find out what kind of variable it is simply by using this. And if you have no idea, you can type of. Let's do type of mix, and it tells us it's a character vector. Okay, so those are really useful to use. Let's just make a logical, we'll call it my logic here. It's a false, true, false. And here we can say is.logical, my logic, answer is true. Okay, if we just type the variable, we can see false, true, false is the contents of the variable. Okay, let's move along. See if we can go back to my slideshow here. So let's go back now, because now you have the context to understand what a data frame is. So a matrix can only be of one type. It can be a character matrix or it can be a numeric matrix, but you cannot mix variable types or storage modes similar to a vector. Right? A matrix is just a two-dimensional vector. But a data frame is more complicated. A data frame allows you to store multiple different storage modes or variable types within the same data structure. So just think of a data frame as really just a sort of an object that's really just a table of data. So you're going to have a column of numbers, a column of character data, another column of numbers. You can have a column of a logical a vector if you want. So it's kind of a compound structure that allows you to store different types of data in one data object. Same really is true for list. In fact, hopefully these two types of variables are distinct, and yet a data frame is a type of list. So without getting too complicated, I think of these as separate, but if you type is.list for a data frame that you've created, say, in this fashion, then you would get true, because a data frame technically is a list. Okay. Although it has its own methods for accessing features of the data frame that are not available for other types of lists. So here's how we would specify data frame at the command line. We would just use our assignment operator here to a variable called data frame. Data.frame is how we define the data frame, or this is a function that allows us to sort of populate a data frame with data. Colors here, this is going to become the column name. So this is a column of colors where we use the combine function for red and blue. Here's we're using our numbers here. This becomes then the column name. And so let's go ahead and do this at the command line just to illustrate quickly how this works. So let's call it data frame. We assign, we apply the function data.frame. We have colors equals red, comma, blue. I can already see I've lost some quotation marks here. And then we have, what was the other column here we had was numbers. So here we have numbers equals C1, comma 2. And now we have a data frame, is.dataFrame. The name of the variable, true it is. Now we can type the data frame right here at the dframe, right at the command line, and that shows us here that we have colors and numbers, and here is our data frame. By default, the row names are assigned to the row numbers by default if you don't specify a row names argument. But here we specified the column names, so we can type column names at any time for the data frame that we just defined, and it gives us what the column names are. We can also type row names, and by default, as I said, you end up with the numbers, or the row numbers become the row names. Okay. So let's carry on. The important thing to note there was that with the data framed object type, you end up with both being able to combine both character vectors and numeric vectors into a single data structure called a data frame. You'll be working with data frames a lot in this class, and as you go along in your careers using R, you will use them frequently. Again, just to summarize, we have these ways of querying what type of variable a variable is. We also have these sort of ways of knowing sort of if this is a vector, a matrix, a data frame, or a list using these ways of querying. So I'll go on. We won't give an example of a list for now. We'll talk about that a little bit later. So what is an R function and how does it work? Well, you've already gotten a little bit of a taste to R functions. We've used the combine function, the C or little c function. We've used the data.frame function, which is how we populate a data frame from scratch. Here I'm just imagining a function that we could write called getGCContent in this class, where we have the seek is an argument. Okay, so this is a named argument where we're passing a value into the function, which is the sequence, and then we're passing the identifier. So this is the name of an individual or a sample. And what happens is the function, its sole job is to return and assign to the variable to the left of the assignment operator the GC content. And we're calling the variable that will then contain the GC content GC. So the function is always called to the right of the assignment operator. And then the output function will be written to the variable on the left of the assignment operator. So again, there's two named arguments, seek and ID, and their input values are the sequence and the name here. So another way to call a function in R, which is pretty typical, is to specify the function, sort of arguments in order. Okay, so here what we could do is we could just say, sorry, I've used X and Y here. I should just put ATGCT, whatever the sequence is, ATGCCGCT here in place of X, and the sample name in place of Y. And if you went to help and saw that this was the order of arguments, then you don't need to specify seek equals, or ID equals this. You can simply specify the values that go into the function, and you don't need to specify the named arguments when calling the function. So, but there you do have to specify them in the correct order, or you will get sort of unexpected behavior. So let's talk about how do you read data in. So for part of your homework, this is one of the things you'll need to do. So you need to read in data as from, say, a tab delimited or comma delimited text file. The table cannot be ragged, so that means that you have to have the same number of columns or fields in each row. So here is a way in which you could simply call or read in a table using the read.table command or function. So here the first argument is the name of the file. If the table has a header, you use the header equals true option, and that will by default take the first line of the file and assign column names, assign the column names to the part of the data object called call names, which we can call at the command line and evaluate. The separator here in our pet example is a tab. It could be comma, it could be anything. We just have to define what it is here. And then here's this case where I've said strings as factors equals false. So in the example we use in this class, many times say it could be DNA sequence, it could be the names of samples, it could be the chromosome name, and oftentimes we don't want to treat those as factors because we're not doing statistical analyses on it really depends on the table, but oftentimes when you want to manipulate text directly, it's easier to not be trying to work as factors, or you want to be working with character vectors. So that'll become clearer later if that doesn't need to be clear now. I just put it here because it's a very common argument to the read table function. So there is one other input format. So this is a format here where all fields are present in all rows. Okay. Another format is where the first row has one fewer columns, and that's a common way of specifying things. Imagine if column 1 was row names but didn't actually contain data, for example. What would happen is you would then only have column names for the data bearing columns, and that format is okay also, but what will happen is that the first column that doesn't have a column header in this case would be assigned to the row names. So typically it's easiest to just kind of get used to working with the non-ragged data, but this is one exception where there is what we call a ragged format because the first line of the file has one fewer columns than the remainder of the file, and that has special interpretation. So I'll let you play with that a little bit, but let's do maybe the more common thing here, which is to open a table. So I'll show you other couple of commands here. So here we can sort of use getWD to see where we are. So we're working a command line here with slightly different functions than in the Usenix command line. So now what we can do is set WD to say my home directory, which I guess we were already in, and now we can do list.files. So here I've made up a directory here called week 3. So we can go to set WD. So we can use tab to kind of fill in using the RStudio sort of shortcuts here. Now we can say, where are we now? We're now in week 3 directory. Let's check out what is in this directory. We have the week 3 table. So let's read this week 3 table in. Let's call it, the variable is going to be called tab, and we'll use the read.table function to read in week 3.table. The separator is a tab separator. We do have a header in this table, so we have header equals true. You could type full true or just T for true. And strings has factors equals false. Notice I use the tab here in this to fill this in, which allows you to sort of work much quicker at the command line. We have return here, so we can say is that data frame table. It should be. By default, that is true. We can check the first 10 lines using a Unix-like command. Here you can see that here's the column, the call names for that table are feature, response, and class. The row names by default, when you notice I didn't specify row names here in the read table function, so by default the row names are the row numbers by default. Okay, so there's the entire table. There's 100 lines, and it just gets dumped to your terminal if you don't use the head command. Okay, so that's an example of how to read in a table, which is something you'll be doing all the time. Okay, so let's go back here now to so that's how we read in data. So how about writing data? Well, writing data, you typically will be writing tables of analysis. So the most common way to write a table of data is to use the write table command. Imagine we just defined a data frame here in such a fashion where we have the column 1 is a vector from 1 to 10. This is a series of numbers. Column 2 is our norm. So all I've done here is to draw randomly from a normal distribution 10 values and assign them to column 2. Okay, so write table is very simple. You specify the name of the data frame, the output file, which we can call test.out. The quote is false, so that it doesn't put quotes around every output value. Row names equals false. These are just some custom settings that I use frequently because I don't like the defaults in R. And the separator here, I usually work with tab delimited files. You can also export simple text using the cat command. But I think for our purposes here, write table will be the default way to output data. Okay, so let's carry on here. So one of the skills that I want you to learn and become really adept at is subsetting, because it is a really important skill in next generation sequence analysis, because oftentimes we're interested in analyzing a set of data based upon some condition, and so we need to take some large data matrix and sort of carve it up, and so that we're only evaluating sort of elements or sort of records in the table that meet a certain set of conditions. And so the way that we can carve up that table is to use what we call subsetting, or sometimes we call it indexing. Let's start with just taking a simple vector of 4 nucleotides, A, G, C, T, and what we can do is subset a vector simply by the index position. So remember here the colon operator, I didn't define it sort of explicitly, but this is just meaning all numbers in between 1 and 2, including 1 and 2. And so in this case, 1 and 2 is trivial because there are no numbers in between, but the colon here means that, let's create a series of numbers as a vector. And so this is a vector that we're now subsetting the basis vector. Okay, so what are index positions 1 and 2? And this is an important point here that I want to make, is that unlike in Bash or in Perl or perhaps other languages you're used to, in R, the first position of a vector is position 1, not position 0. Okay, let me repeat that. That's what in R vectors are 1 based or 1 indexed. That means that the first position of the vector is a 1, not a 0. So if we want to extract position 1 and 2 in this case, we can specify a vector 1, 2, and that would return the values or a subsetted vector. Let's just do this really quickly. We'll define a vector called bases. We have A, T, whoops. Oops, I keep hitting the wrong button here. Okay, G. So there's our vector bases, right? this is a character vector. We can create this is how you create a vector as a series. Okay, you can do the same here just to convince you that's how you create a series. But what we can do here now is just to subset out the first two positions. Okay, again, it's one based, so we can do bases just position 1, like so. Okay, so this is how you index using numbers. Of course, we could do 3 to 4, same way. So, so here we can define these first two bases of the purines, the A's and G's. The pyrimidines are positions 3 and 4, or C and T. So we can index using numeric positions or index positions of a vector. We can also subset a vector using a logical. So here, sorry, this is a typo. This should be bases. If we use bases here, again, we can have a vector, a logical vector, true, true, false, false, and that will return the first two positions of the bases. Sorry, again, pets was a variable I was using in a previous lecture. This one here I'm using, we like to use bases. So let's go ahead and give that a try. We go back here, now let's do bases, and let's just type in our logical vector. And this is important, it's kind of trivial here, but it's important conceptually, and I'll explain why in a second. So bases here, again, true, true, that means we want the first two positions from the bases vector. False, false means we don't want those positions, obviously. So now let's do something a little bit more complicated. Let's say we want to subset a data frame by row position. Okay, so here what we can do is, what's important here is that in this notation, dframe bracket 2 comma, okay, the comma here is separating the rows on the left from the columns on the right. So if we specify 2 comma, that means what we want is row 2. Empty in the columns means all columns by default. Okay, so then here if we wanted, say, column 3, but all rows, we would specify a blank for the rows to the left of the comma and a 3 to the right of the comma, which is specifying column 3. Another way we can subset, sort of just pull out a column or a row, is to use the row name or column name. So here in this variable, or in this data frame that I've created here called dframe, notice we have 3 column names: chromosome, position, and rand. Again, rand, I just pulled out 3 random numbers from a normal distribution. Again, what we could do if we just wanted to pull out from the data frame the rand column, we can use the name of the column to extract the column rather than using the index position. So sometimes we don't know the index position or what column number we want. We know the name of the column, and this is how you access it. So here's where things get a little bit more complicated, but I definitely want you guys to understand this. Okay, so the important thing to note here is that, is that we can use what are called conditional statements, okay, to return logical vectors, which allow us to then use the logical vector syntax to extract rows, in this case, of data that meet the conditions we're interested in. So that sounds complicated. Let me give you an example. Okay, so let's say that we want, okay, in our table here, these are our column 1, we have features, 2 we have what we call response, and 3 we have class. Let's say that we want, for our response here, we want all values that are greater than 0. Okay, so what we can do, first of all, just to convince you, is we can take tab, the column here, which I spelled wrong, is respond, and what we can do there, that's going to return the 100 values that are in that column. Okay, but now let's say that we want all where they all are greater than 0. Oops, greater than 9. How about greater than 0? You'll notice here that we have a mixture of trues and falses. Okay, so now let's imagine that we want to subset a table of all values where we want all rows in which the response column was greater than 0. So how do we do that? Well, the way that we can, let's call a new variable called subtab that meets our condition, and we can have data frame, excuse me, this one's called tab, and we have all rows where the tab column called response is greater than 0, comma. Okay, so what this, let's digest this because this looks complicated, but it's not. Okay, remember, I just typed tab and this column greater than 0, and we got the logical vectors here. So what this is going to do, this command here is we're simply inputting a logical vector which says which rows to the left of the column that we want, which are all true. Okay, and then we want all columns. Okay, and that's why to the right of the comma we don't have any values here. So let's give that a try and see what we get. So now if we look at what subtab has in it, notice that all the values in the response here are greater than 0. Okay, so and then here the row names, remember, were the row numbers in the original tab data frame. So this is, I want you just to kind of stare at this till you kind of understand it, because it is an important skill. And we'll be developing it over time. You'll be using it in your homework for this week. But notice again, let's just one more time. There's a comma here. We're working to subset the tab data frame. Notice the comma here, which means that to the left are the row arguments, where we're trying to specify the rows that we want using a logical vector. And we want all columns in this case, because we want to just output the same data set simply with the rows that meet this condition. So this is an input logical vector, because the conditional statement here greater than, these conditional statements always return logical vectors. Okay, so we input a logical vector here for this for the rows, and this will return just the rows that we want. Okay, I'm going to leave that for you to digest a little bit. Let's go back here. We're about to wrap up the lecture, this first lecture, but let me find my slideshow here. Sorry for the confusion. So one other thing, sometimes to make the syntax a little easier here, the $ here is the syntax for the name of the data frame, the name of the column name that you want to subset on, and in this case we're subsetting on, in this pet example, numbers greater than 10 in this column, and that would extract all columns whose rows meet this condition in column, the positions column. Okay, so this is a little bit complicated. It's a little bit hard for me to say in words sometimes. So if if you go back and my words seem a little bit confusing, I think conceptually it's fairly clear. But let me know if you have any questions, and I'm happy to help you. So finally, I'd like to introduce two final concepts here. This is important for R sessions. So when you open RStudio or R generally, you are implicitly creating a session. There are ways in which you can sort of access your files structure on your computer using these commands which I illustrated. You can also sort of query or identify what variables are defined in that session using the list command, just like it's similar to the command in obviously in Unix, but we're not looking at listing files, we're listing the vectors or the other types of variables that are defined at the moment in your session. We can remove a particular variable. Let's say we want to get rid of that subsetted table. We can remove that, and now if we check, now we don't see subtab anymore in this session. We can remove all values from a session using rm with the list argument. ls is blank, and that would remove all defined variables. Now, One thing that's important to understand is that you can, when you exit or quit a session in R, you can type quit, okay, or just Q rather. And now notice that we're prompted for save workspace image to week3.rdata. And that if we blow it up here, it's asking us yes or no. Let's say yes. And so what it just did is it saved the session in a file called rdata. Okay, if you then type load path to rdata when you then relaunch your session, or excuse me, when you relaunch the RStudio, what you can then do is just open that rdata.rdata file, and what it will have in it is all of the data with all of the variables from your previous session already defined. Okay, so we've simply just reloaded that same session as if we'd retyped that session again. So I think this should be, by default, this is going to be a capital D for our data. But anyways, I hope you get the point that you don't have to lose all of your work that you've worked hard in your particular R session. You can save it, reload it, as if you just typed it again. Now finally, I thought I'd throw just an alert here to, it's important when you're working with R, as really with any type of data, how are you handling missing data? And in R, the most common way to handle it is with the NA string. In the end, NA really is sort of a special character here. So let's make a variable called numbers. And let's add an NA here. Notice no strings or no quotes around the NA string. It's simply NA, otherwise R won't interpret it correctly. So now we can type numbers. You can see that NA is there. And now let's see if we do something in is.NA. This is an important function that returns a logical vector with the positions that evaluate to true where there's an NA. We can also do the reverse. We say not is.NA. And what do you think that's going to say? Well, probably you expected. True, true, false, true. So it's the inverse of is.NA. But let me give you an example why this is important to understand. So let's imagine that you use the sum where we just want to count, we want to add up the numbers in the numbers variable. So let's do sum numbers. The answer is NA. So why is that? And this is why it's important to understand that R by default within the sum function returns NA if there are any NAs present, because it wants you to specifically state how you want to handle NAs. And here we can use the argument na.rm equals true, and then we get the expected behavior. So this is a case where, just doing sum and checking out how, the function works. Notice that by default, na.rm equals false, and if the NAs are not removed, then by default, the sum function returns NA, which might not be expected behavior if you're working with a large data set where you don't know if there are NAs or not. So part of working effectively with large data sets is to understand in exquisite detail what each of the data types are, whether there's NAs present, and how you're going to handle those NAs. Okay, so with that, I'd like to close this lecture. Tune in to the next lecture for another sort of round of introductory material in the R statistical programming language.